Good morning, everyone. This is the technical session 4, and I'm Radha Balakrishnan. Good morning, and again. And there are going to be 3 talks in this session. And the first speaker is Professor M. Lakshmanan from Center for Nonlinear Dynamics, Bharatidasan University, Tiruchirappalli. And the title of his talk is Genesis and Progress in LPD Equation. LPD stands for Lakshmanan-Porsezian Daniel Equation. Professor Lakshmanan.
So thank you very much, Professor Radha Balakrishnan. And the title of my talk is Genesis of and Progress in LPD Equation. So in this talk, I will briefly explain the genesis of LPD equation. It's essentially a tribute to Porsezian, who is no more there, who passed away unexpectedly 2 years ago. Porsezian and Daniel were my former students, and we essentially identified this equation as early as in 1988 and identified the associated integrable spin chain. This equation is drawing a lot of attention in recent times, both in nonlinear optics and in ferromagnetism. So in this talk, I wish to point out the recent progress in understanding the nonlinear dynamics of this equation and related non-integrable system. So this was the original paper by Porsezian, Daniel, and myself, in which we started looking at the effect of discreteness on the Heisenberg spin chain, and its follow-up paper almost 4 years afterwards in 1992. But why it took so much time, so I'll point out in due course. So that was the aim. That is the aim of my talk, to present an overview of this LPD equation and the recent progress. So to start with, I will introduce the model and the dynamical equation and introduce the so-called space curve mapping and reduce the invariant equation to obtain this LPD equation. And then, in order to analyze the integrability property of this, so I will carry out a Painleve singularity structure analysis very briefly and identify the parameters for which this is Painleve integrable. And I will also show that this is lattice integrable for the same parameter values, both for the LPD equation and the associated spin chain. And then I will point out what are the present developments in this equation. So to start with, I consider the Heisenberg spin chain with nearest neighbor bilinear and biquadratic interactions. Bilinear interaction Si dot Sj. Nearest neighbor interaction J is the exchange integral. And biquadratic interaction with the interaction parameter K. So Si dot Sj square. So sum over the nearest neighbors, where the vector Si is a unit vector with three components, Six, Siy, Siz. One can deduce the spin equation of motion by identifying the Poisson bracket for two functions of spins A and B. So the Poisson brackets of A and B can be written in this particular form. So making use of this Poisson bracket relation, one can deduce the equation of motion for the spin chain as dsn by dt, the Poisson bracket of Sn with the Hamiltonian H, which turns out to be Jsn, vector product of this quantity Sn plus 1 plus Sn minus 1. That corresponds to the standard bilinear Heisenberg spin chain, and the term proportional to K, the biquadratic exchange interaction. So you have this spin equation dsn by dt equal to this right-hand side, the last equation. Now, this equation as such is difficult to solve, and probably it's not integrable. Then one can consider its continuum limit by looking at the continuum limit x. If you consider the nth interface then you can x equal, and in very long t going sub t, the continuum based on plus or minus 1 as a Taylor series, and obtain the continuum equation up to order A4 as S of t is S vector product S of xx, which means second derivative d square x by dx square. So that is the standard Heisenberg spin chain in the continuum limit. And the next order correction, the fourth order correction is gamma 1. Gamma 1 is a square by 12. A is the interspace lattice parameter, which is quite small. And then the biquadratic exchange term, gamma 2 is ka square by 1 plus 2k with this particular term. So I would like to consider whether this system is integrable. And what are the integrability properties? What are the underlying, the structure of the underlying solutions and so on. When the parameters gamma 1 and gamma 2, gamma 1 is a square by 12, gamma 2 is ka square by 1 plus 2 ka. So you have the parameter A, the interspace interlattice parameter, and gamma 2 involves the biquadratic exchange parameter also. When both gamma 1 gamma 2 equal to 0, then you have the standard isotropic Heisenberg spin chain, and that has been proved to be completely integrable nonlinear dynamical system possessing soliton solutions and is equivalent to a nonlinear Schrodinger equation as early as 1977. Then you have a unit spin vector S, and which is a function of the component X and Y. Okay, so this upper index X corresponds to the components, but the lower index X corresponds to the derivative with respect to spatial coordinate X and spatial coordinate T. Okay, so ds by dt equal to S cross d square S by dx square plus gamma 1 d power 4S by dx power 4 and so on. So I would like to consider that particular equation. Since S is a unit vector, I can map this unit spin vector as the tangent vector of a space curve and define the principal and binormal vectors E2 and E3 to complete a local coordinate system, so that you have the standard Serret-Frenet equations for the spatial variation EIX equal to D vector product EI, where D is the vector kappa E3 plus tau E1, where kappa and tau are the curvature and torsion. So kappa is the curvature, E1x dot E1x power half, where E1 is the first unit vector, tangent unit vector E1. So E1 derivative with respect to x, so E1x dot E1x, so power half is the curvature, and torsion, how much it deviates, so the torsion tau equal to kappa minus 2 E1 dot E1x vector product E1xx. So that's the standard notation of the curvature and torsion for the standard space curve. As one is familiar with respect to a fixed coordinate system, you can identify a moving coordinate system with the origin O prime, and you can consider the unit trihedral E1, E2, E3. And the variation, spatial variation, is given by the Serret-Frenet equation, and you can identify the temporal variation. For example, if you consider just the standard isotropic Heisenberg equation ST equal to S cross SXX. So identifying S with E1, so you have E1T equal to E1 cross E1XX, but E1X is kappa E2X from Serret-Frenet equation, and then you take the derivative. So you have E1 cross kx E2 plus k E2x and E1 cross E2. So you have E3 coming up and E1 cross E2x, you have E1 cross minus kappa E1 plus tau E3 coming from ferromagnetic equation. And so E1t you can write as kappa x E3 minus kappa tau E2. Then you can identify E2t and E3t. You can complete the evolution of the trihedral. Similarly, for the equation with biquadratic term, then you have EIT equal to vector omega cross EY, where omega is omega 1 E1 plus omega T2 plus omega 3 E3, where omega 1 involves now the fourth derivative with respect to, of the curvature and torsion, etc. So you have omega 1, omega 2, omega 3. So you have the spatial evolution as the ferromagnetic equation and the temporal evolution as this equation EIT equal to omega cross EI. Then you can take the compatibility of these two sets of equations and you can obtain the evolution of the curvature and torsion, which is related to the evolution of the energy and current density. So you can obtain an evolution equation for curvature and torsion, this fourth derivative equation, which is quite complicated, etc. However, you can make a complex transformation instead of kappa and tau. You define a new variable, a complex variable q equal to kappa by 2 exponential I integral tau dx, and which leads through which you can reduce this set of equations for curvature and torsion evolution as a simple equation for the complex quantity q iqt plus qxx plus 2 mod q square q, which is nothing but the nonlinear Schrodinger part, and then this fourth derivative part, which involves these two parameters gamma 1 and gamma 2, which corresponds to the lattice parameter and the biquadratic change parameter k, which I have written earlier. So you have this 5 parameters coming into the problem along gamma 1. But essentially, there are 2 parameters, gamma 1 and gamma 2. So when gamma 1 and gamma 2 are 0, then you have the nonlinear Schrodinger equation, which is equivalent to the Heisenberg spin chain. But when you go to the next order correction, you have this fourth derivative equation. You don't know what is the nature of this equation. In order to understand, identify whether this underlying system is integrable or not, one can carry out a Painleve singularity structure analysis of this equation. So by writing an equation for Q and Q star. So actually, when you write an equation for Q, it's for a complex variable, and so you have the corresponding equation for Q star. So I write these two equations in terms of the two separate functions E and G, and ask check whether it's integrable by looking at the Laurent expansion of these two variables E and G. So I try to assume the solution to be in the neighborhood of singular manifold, complex singular manifold, phi as a characteristic manifold, phi as a Laurent expansion in the neighborhood of it, and ask whether such a series expansion exists. And the task is to find the leading order and the resonance, that is the powers at which the arbitrary functions enter into the series, because you have a fourth order partial differential equation. So you will have to identify sufficient number of arbitrary functions and then check whether the series exists and so on. So this is a standard Painleve analysis, which came into existence in the year around 1980s by Weiss, Taber, and Carnival. They gave a prescription. So you can look at that. First, you can look at the leading order, and you will find the leading orders. P take the values P, and S take the value -1. And at that power, at that order, you find the leading order coefficients E0, G0 have this form. Two possible expressions for leading order. And then you try to find the resonances, powers at which arbitrary functions can enter. So if you try to look at that, then that becomes the resonance equation becomes quite complex. And you have to try to analyze these equations, and they take in general complex forms, which means introduction of movable singular manifolds, critical manifolds, and so the system will not admit integrability property in general. But then you identify a particular value. So in general, for possible values, you find singular manifolds arise, but for a specific value of the parameters gamma 2 equal to minus 5 by 2 gamma 1, you find the resonances are real, minus 1, 0, 1, 2, 3, 4, 5, 6, etc. There will be two sets of branches, and you identify that at this powers, arbitrary functions do arise. In fact, you can check that at j equal to 0, you have E0, G0 equal to minus 5x square. At j equal to 1, you have this, and at j equal to 2, you have this, and you can check that sufficient number of arbitrary functions arise. And as a consequence, you identify the Painleve integrable form of the evolution equation at the next order correction for the spin chain as this form IQ2 plus QXX plus 2 mod Q square Q equal to into gamma is fourth derivative terms. So, and this equal to 0. So now this equation is now one finds as a lot of interest in optical physics. One can identify this second derivative term corresponding to group velocity dispersion, higher order dispersion, and self-steepening, self-frequency, and quantic interaction. Similarly, from ferromagnetic point of view, one can identify this as a dynamical balance for an alpha helical protein, for example, due to resonance interaction and so on. So this is the integrable LPD equation from Painleve sense, and the corresponding spin chain equation is this fourth order spin chain equation. When gamma equal to 0, then this is the standard Heisenberg spin chain, and when gamma equal to gamma 2 minus 5 by 2 gamma 1, then you have this spin chain equation. And for this equation, one can show that this is lax integrable by identifying the appropriate eigenvalue equation Vx equal to U1V and the corresponding time evolution Vt equal to U2V. And you can carry out an inverse scattering transform analysis. Similarly, for the spin chain, one can identify the corresponding eigenvalue problem U1 equal to minus I lambda S. S is S dot sigma. Sigma is the Pauli matrix, sigma 1, sigma 2, sigma 3. Similarly, for the time evolution part, you have U2, this particular form. And once you have this, you can carry out an inverse scattering analysis, or you can carry out a Veclan transformation, or a Darboux transformation, and so on. You can identify, for example, the one spin, one soliton solution as Q1 minus 2 eta. 1 eta is an arbitrary constant, secant h hyperbolic secant h Z1 e power I 2I F1, where Z1 involves the spatial variables and time variables in this particular form, and F1 has this particular form and so on. So this is the one soliton solution on the fourth order partial differential equation, this LPD equation exact solution. And you can proceed further to get multi-soliton solutions and so on. Similarly, for the spin chain, you can obtain the spin solitons Sx, Sy, Sz, the one soliton, and you can construct n soliton solutions also. Yeah. So this is the, for example, this is the one soliton solution for the Q variable. Okay. And its projection, you can identify this is mod Q square. It is localized structure, localized in space around X. Okay. And you can identify breather solutions. So you can obtain, for example, first order breather solutions, which temporally is periodically oscillating and spatially it's localized structure. So you can obtain exact one-breather solution. You can obtain multi-breather solutions, etc. So all these solutions are being identified in recent times. And as a limiting case of this breather solution, you can obtain a rogue wave solution. So a rogue wave is a double localized high-pitch structure which is supposed to approach from nowhere and disappears without a trace. So standard definition of a rogue wave, because you have this form where you have the limiting form where you have the variable x and t, as x and t takes large value. So this disappears with a finite at a finite background. So that's the first order rogue wave. You have second order rogue waves and higher order rogue waves with their internal structures, etc. You can identify. Now, in recent times, considerable work is being pursued on this LPD equation, but different types of localized solutions, including multisoliton solutions, periodic solutions involving elliptic functions, theta functions, etc., are being explored, and their analytic structures are being identified. One can work out a perturbation analysis to obtain a general solutions of the general LPD system, not with that specific choice gamma 2 equal to minus pi by 2 gamma 1, but even for general parametric value. One can work out a Riemann-Hilbert problem, a generalization of the inverse scattering problem by giving the appropriate structure of the eigenfunctions and then tracing out the nature of the solutions Q or S, the spin variable. So Riemann-Hilbert problem has been extensively studied for the LPD system for more general initial conditions. And one can also consider vector generalization of LPD models. And in recent times, nonlocal and fractional order differential equations also have been considered. For example, during the past 2 years, many works have appeared in the literature considering various aspects. For example, you have the nonlocal LPD equation with the same structure, but with appropriate changes in the spatial variables Q star minus xt at different terms and so on. This has been analyzed, and different kinds of solutions have been obtained. Fractional order is introduced in order to incorporate the memory effects and the hereditary consequence of the system. So by considering fractional order derivatives for time, fractional order time derivatives, for example, I dt mu, where mu can take some fractional value. It need not be just one, but it could be some arbitrary value. So arbitrary value, so not necessarily integer. So fractional values it can take. You can consider such fractional order. You have a different definition of fractional derivatives. So you have a Caputo derivative. You have other kinds of many definitions of fractional order. So Caputo derivative, for example, in the sense of Caputo derivative, this equation has been analyzed in recent times. Soliton solutions and other kinds of solutions have been obtained. One can consider coupled LPD equations of different orders. For example, two coupled Lakshmanan-Porsezian Daniel equation of this particular form has been analyzed in recent times, but three coupled, even n coupled equations have been analyzed in recent times. Their Lax forms, eigenvalues, etc., have been worked out, and the underlying solution structures have been deduced, etc. So one finds the LPD equation as is drawing considerable attention among nonlinear optics and magnetism communities, and it's being generalized in different directions. So but still, there are lots of open problems. For example, the general LPD equation remains analyzed for its all possible nonlinear dynamical structures. If it is non-integrable, then what is the underlying structures, nonlinear structures it can admit? As I have tried to point out in my analysis, that even though it may become non-integrable, but still from the perspective of moving space goes, certain linearizations are possible, but whether that kind of linearization can lead to some nice structures, that remains to be analyzed. So non-integrability, chaos, and other kinds of patterns in such general LPD equation remains to be analyzed. So much work remains to be done on these aspects, and I do hope that in the near future such aspects will be analyzed. I think at that, this is the right time for me to stop. If there are any questions or comments, most welcome. Thank you very much for your attention.
Thank you, Professor Lakshmanan, for a very beautiful talk.